I'm going to talk about topological embeddability, mostly between continuous functions. I'm going to give a short kind of introduction and motivation of why we started looking for the main results with Zoltán and Yann Pequignot, who was here 2 years ago. And okay, so first, my framework, I'm always going to work with Polish zero-dimensional spaces. So I'm not going to write it ever, but like the variables x, y, or z are always for Polish zero-dimensional spaces. And for me, a good example of such a space is a countable ordinal with the order topology. So whenever there is a countable ordinal on the screen, I always consider it as a topological space with the order topology. Then, sorry, what?
What happened to the counter space?
It's another example, but
okay,
it's a perfect example.
It's a perfect example.
Why did you write the third thing?
That's a good one.
Yeah, I left the third thing after, like, so I gave this talk in seminars before, and systematically I had the question, what do you mean by this notation? So, I don't know.
Well, category theorists ask the question.
Well, I gave it in computable analysis seminars, and there apparently
I don't know the standard notation for a function.
it's not that. It's like they have.
Like, why does a set theorist use our type theory notation?
For instance, so I don't know. I just decided that from now on I would include this.
In what sense is Cantor the universal Polish zero-dimensional space?
Huh? What do you mean?
It's not compact.
For compact ones, right?
Yeah. Oh, I should have said compact.
Yeah.
Comparison.
So every compact Polish zero-dimensional is homomorphic to a perfect. No, but closed subset of the Cantor space, right? Okay. Then, yeah, I just recalled the definition of an embedding. I will say embedding. I always mean topological embedding. Where I don't mean model theoretic embedding. And yeah. Okay. So what? The last. It's an equivalence of embedding. Right? Okay. So our main definition is what an embedding between two functions is. So it was defined, well, first like explicitly, I think, by Zoltán, it's in the picture here, in '98. But it's a quite natural notion. So you say that F embeds in G if there's a pair of embedding sigma and tau, such that tau F equals G sigma, right? So the diagram there commutes, and we're gonna write it with the square subset symbol.
And it means in some sense that F is simpler than G.
It means that F is simpler than G in the sense that there's a copy of F on a subfunction of G. Yeah. Okay. So yeah, and sigma is defined from x to x prime, but tau is not defined on the whole space Y. It's defined just on the image of F. So one has to be careful about that. And it's very important.
As you told me last time, this is different than the graphs embedding topologically one another, right?
Yeah. It's different. Yeah. This is stronger because so it's quite easy to see because, for instance, this notion preserves the Baire class. So and graph embedding, like embeddings of graphs, doesn't, because you have functions from arbitrary complex Baire classes with closed graphs, so bi-embeddable graphs. Okay, So the first thing to kind of warm up. So it's obviously a quasi-order, meaning that it's transitive and reflexive relation, embeddability, and it was first considered to prove basis results and even like finite basis results. So a basis is just a set of minimal element for some class, right? And so I would just like to sketch the proof of these three. So the third one is not a basis result, but it's the only maximal function result that one of the only that we have. So the first one, the identity is minimal for all Borel function with uncountable range. So how can we do that? Well, so this is for the first one. Take f from x to y, and the image of f is bigger than Lf0. And so what we do is we look at the equivalence relation on the domain of f. X is equivalent to y if and only if f of x equals f of y. And so this is a Borel equivalence relation on a Polish space. We can apply Silver's dichotomy. And there is more than Lf0 many classes. This is exactly what this hypothesis says. So by Silver's dichotomy, we can find a small compact set K0 in the domain of X, in the domain of F, such that K0 is homeomorphic to the Cantor space, and F restricted to K0 is injective. This is given to us but for free by Silver's dichotomy. Okay? So now f restricted to K0 is a Borel injective function, as like Ben, for instance, reminded it an hour ago. Every Borel function is, when restricted to a density delta, is continuous. So I can just take a further compact subset of K0 on which f is not only injective but also continuous.
What's Silver's dichotomy again?
Sorry, what?
What's Silver's dichotomy again?
So if you take a Borel equivalence relation, it has either countably many classes, or you can, it reduces the identity on the Cantor space.
There's a perfect set of representatives, in simple words. And it's for pi 1, 1, I think, right? Even
yeah. So take now K1, put it in K0. K1 is once again homeomorphic to Cantor.
We always have this conversation. You didn't actually need Silver's dichotomy?
No.
So why not?
Well, I guess you can use the Kuratowski-Ulam result, but like.
Yeah, but this is for how?
I mean, I never really bothered because, to be honest, because Silver's dichotomy gives it like in.
There was some thing that people knew long before Silver's dichotomy that was sufficient, but I don't remember why on page.
So I didn't follow the end of this. So f is now injective and continuous.
Yes. Wait. It's not. I haven't. I wasn't done yet. Such that f restricted to K1 is injective and continuous. So being injective and continuous, it's an embedding. So f restricted to K1 is an embedding. So what I'm going to do is I'm going to take sigma, an embedding, and now I just build, so this is the identity in Cantor space. This is F, put sigma here, and here I put sigma and F. And this is, okay? So these are the two embeddings needed to embed the identity into F.
But it's just the perfect set there. The image of the set is uncountable.
It's an analytic set.
And then you still, I guess you still want to choose. You want to choose over an X, but you can do that. You can just use Jakob von Neumann to choose in a sigma sigma one dimensional way, and then you go down to a comeagre set where it's for F.
Yeah.
That doesn't sound.
Well, the point is that everything I just said was known in the 1930s.
Yeah. But as I said, it's just the first result. So, okay. So now the second result, F0, F1. So F0 is the characteristic function of the singleton omega as an element of omega plus 1. And F1 is any bijection from omega plus 1 to omega. So they're both like the simplest example you can think of for discontinuous functions. And as a matter of fact, they're a basis for non-continuous functions. So how are we going to do that? You take f from x to y, discontinuous. And so you take xn in x that witnesses the discontinuity of f such that xn converges to x and f of xn doesn't converge to f of x. And now you look at the direct image of the xn's, and either it's infinite or it's finite. If it's infinite, you can go down to a further subsequence where f on which f is injective, right? So case 1, f of xn is infinite. So go to a subsequence such that f restricted to xn is injective, and is 1, 1, and also you can also suppose that this the image of this subsequence is actually discrete. So and it doesn't and separated from the image of x. By an open set. Okay, and now you just say that sigma of n equals xn, sigma of omega equals x, and which direction did I want to say? Yeah, and you notice that such a sigma is an embedding, and now you just say tau of y of tau of, let me say it this way, tau of f of x equals g sigma of x defines tau, and you have an embedding, and sigma tau embeds F1 in F. Okay? Oh, not G, F. Thank you. This was F1 and this was F. Yes. Yes, thank you. Okay.
X is the limit point.
F1 of y for all y. Thank you.
For all y, what does it say?
For all y, tau of F1 of y is equal to G sigma of y. So this is a remark that will be very important. Is that the remark is fix. It's F.
Oh, F.
Yeah. So if you fix, the remark is if you fix sigma F and G three functions.
No, sigma is defined on the natural numbers, not on the xn's, right?
Yeah.
So y.
Now we're here, we have F, we have F1, here we have this, and this, right? Right, and now what we have is that sigma takes an n and it maps it to xn, isn't it? I wrote it the other way. No, I wrote it the right way. And omega to x, right? Now, because of my choice of these points, I know that sigma is an embedding, and given, and this is a general remark, given three function and like this, there is at most one function that makes the diagram commute. So the only thing is you have to prove that this one is an embedding, but this one is from omega to a discrete space, so it is an embedding. Okay.
And this is now the this is the tau.
This is the tau.
F1
Yep.
of y. F1 is at omega.
Yes.
F1. No, sorry. F1 is.
F1
is the spaces. Yes.
Yeah.
Okay.
Okay.
Is f of sigma.
In the other case, you're constant, and then.
Yes. Okay.
Exactly. In the other case, so the case 2 is the image f of xn is finite, and then you pick a subsequence such that f restricted to the subsequence is constant, and you do the same trick, right? So pick a subsequence such that f restricted to xn is constant, and do the same trick. Okay. So that was point number 2. And point number 3 is that the second projection is maximal among continuous functions. And this is just because if I'm taking, so here is space, this is now F, and this is P, and okay, what I do is I take X, I map it to the pair X, F of X, and here I put the identity.
Okay, that's interesting because it tells you f is not so much simpler than the function it reduces to.
Yeah.
This is n
Oh, yeah, thank you. Okay. And so this was actually, I was interested in topological embeddability because I was interested in the existence of a nice quasi-order on functions in general. And I was drawing inspiration from the wage quasi-order, and one of the nice features of the wage quasi-order is that every class sigma 0 xi has a maximal element for the wage quasi-order, so that's really nice. And I was wondering if it was the same for topological embeddability. And one of the things that we proved with Zoltán and Yann is that the continuous functions is actually the only bare class for which there is a maximal function for topological embeddability. So all the other bare classes have no maximal elements.
That's too bad.
Yeah, that was the, but there is more bad signs for the topological embeddability. It gets worse. Okay. So further finite basis results, just recall the definition of a bare class 1 function. It's sigma 0 to measurable, and a function is sigma continuous if it can be covered by continuous functions on Borel domains. And
Bare class 1 is the same as pointwise limit of?
Yes, if your domain is zero dimensional or if the range is R.
Okay.
But you have to, this is why I wanted to talk about sigma 0 to measurable.
And that means a pre-image of open sets is sigma 0.
Yes.
Didn't you say that all spaces are zero-dimensional?
Yes. This is why, you know.
What is it
So
about
R
the
is not
range
a
that you
space.
need when you say the range is R? I mean, I'm just curious.
Because this fact that sigma 0 to measurable functions are exactly the pointwise limit of continuous function, it's also true if the range is the real line.
The real line.
Yeah, the real line, not the bare space, the real line. Okay. Yes, didn't I write it? Oh yeah, okay, that's a typo. It's countably many continuous functions. Yeah.
Otherwise, much less interesting.
Yeah, otherwise it's any function, so yeah. Okay, thank you. So you fix the, so this bijection F1 we had, if we take the infinite product of it, then its domain is now omega plus 1 to the omega, and the range is the bare space. But omega plus 1 to the omega is just like another compact perfect Polish space, so it's another version of the Cantor space. And what Zolecki and then Pawlikowski and Sabok proved is that this function P for Pawlikowski, it is minimal among all Borel non-sigma continuous functions. So Zolecki proved it first for not for the class of all Borel non-sigma continuous, but for the class of bare class 1 non-sigma continuous. And then Pawlikowski and Sabok just extended that to all analytic function on analytic spaces actually. But okay, so this was actually the original motivation of Zolecki's, I think, for introducing this quasi-order of embeddability on functions. Okay, then with Ben, a few years back, we showed that there's a 3-element basis for all functions with domain irrationals.
Hard? Is that hard?
Are you Miller?
Yeah.
That's not hard.
That's trivial.
If you say so.
No, I don't.
I mean, if you have a one-line proof, then yeah, sure. But I'm not sure there's a one-line proof. You still have to write it. It doesn't use any big technology.
It's uncountable.
Oh, yeah, but like this is more the second result. But this is why I mean, it is another finite basis. I didn't mean more than that.
Difficult than the second one.
Yeah.
Okay, that's all I meant.
Yeah.
Sorry, what is the difference between 1Q and IDQ?
1Q is a constant on Q. And IDQ is the identity on Q, right? So the three-element basis is a constant, the identity, and just the function that discretizes Q. So you take Q and you biject it with N. Okay? And
one of these three is below any other.
yeah. Okay. Yes, because one of the strange feature of this quasi-order is like if you have an injective function, what's below an injective function has to be injective. And so what's below the constant on Q cannot be below the identity, for instance. And also the discrete function cannot be below the identity because it's not continuous and the identity is. And the identity cannot be below the discrete function because the range of the discrete function is too simple. Right? Okay. And yeah, so when knowing about all these basis results, you can wonder, okay, well, this is great to have finite basis, and it's even greater to have actually to know exactly the finite basis. But these results would be really weaker if there was always a finite basis. So this was a very natural question, and another way of phrasing it is to ask if topological embeddability is a well-quasi-order. So well-quasi-order is a quasi-order without infinite anti-chains or without infinite strictly descending chains. But it's equivalent to saying that every upward closed set has a finite basis. Yeah, because like if you have, so in one direction, if you have an anti-chain, then it has no, the closure upward has no finite basis. Same thing for an infinite descending chain. And if you have an upward closed set with no finite basis, then you say, does it have a basis? If it has one, it's infinite, so there's an anti-chain. If it doesn't have a basis, then you can construct an infinite descending chain. Okay, so.
Can you go back to this previous one? There were the 6 elements which you didn't give.
Yeah.
I assume they're all very simple functions.
Yes, so the idea is you have these, the idea is that you have these 3 elements for the basis for functions on Q, and then you have a 2-element basis for function from bare space to bare space, which is the constant and the identity. And you mix these 2 bases, you take any possible combination, and yeah, it feels close to 6. Yep. Okay. Okay, so anyway, I was asking this question actually at the Young Set Theory workshop a few years ago in Copenhagen, and actually Zoltán managed to come up with an infinite anti-chain of continuous functions within like 2 weeks, and he sent me a file with an example of the infinite anti-chain, and it was a very good idea, but I thought it was nicer to give a picture with a graph, with an actual finite graph. I'm going to give you the picture in a moment, but so I just rewrote a little bit what he had sent me, and I talked about it with Yann, and then we met at Toposim in July, and we discussed about the example, and Yann was saying, yeah, but if you have this example with finite cycle, why do you stop there? And you should just prove that any graph can be coded as a function. And so this led to this dichotomy. This is a kind of packed together version. So the dichotomy is like if the domain is compact, then either we have a sigma 1,1 complete quasi-order. So it means that any sigma 1,1 quasi-order reduces to topological embeddability, or it is WQO. So now what you should observe is that being sigma 1 complete is, for a sigma 1 quasi-order, is as far as you can go from a WQO. Because for instance, a sigma 1 complete quasi-order reduces the identity quasi-order on the natural numbers. It reduces the identity on the Cantor space. It reduces...
Diagonal?
Yeah, the diagonal.
What is that? What quasi-order? The quasi-order where...
Of the diagonal, just like x is equal to y, the equality. Yeah.
Why is that bad if it reduces that? I mean,
Well, you have an anti-chain for sure.
oh, yeah, that's true. Yeah.
And if you look at the identity... Reduce, yeah, reduce is... it's written here, right? So reduce means that you have a function from your base space, the base space of the first quasi-order to the base space of the second quasi-order, such that two elements are related if and only if their images are related, right? So, for instance, if you reduce the equality on the natural numbers, well, for sure, in the image, you'll have an infinite anti-chain. But it gets worse because the equality on the Cantor space is just a perfectly closed quasi-order. And the lexicographic ordering on the Cantor space is also a very simple quasi-order with a lot of infinite descending chains. And these are only closed. So if you're sigma 1 complete, you will reduce not only all these ones, but all the more complex one that you can find among the analytic quasi-orders.
And reduce always means with continuous functions.
Yes, yeah. Yeah.
What is the definition of reduce?
Yeah. Reduce for me is not necessarily continuously, but I'm gonna write it down.
A nice example of a sigma 1 complete quasi-order is embeddability of countable structures.
Embeddability of countable structures. Yeah.
That's at the top. And that's Louveau.
I'm gonna use that as a matter of fact.
Yeah.
And yeah, and
You said you're just doing graphs, right?
yeah, but it's in the same article. So okay, so now I'm going to unpack this.
Embeddability of countable graphs.
I'm going to unpack this theorem here, and what we prove is exactly these 3 points. So as I said before, I'm going to use the space of countable graphs. So a graph for me, I don't want to specify it all the time. So a graph for me is irreflexive symmetric relation on the natural numbers. And so I will always consider it as just a subset of pairs. Okay?
A set of unordered pairs? Is that what that means?
Yeah, a set of unordered pairs. Yeah, this notation, is it this here? This notation means unordered pairs. And so there's a nice Polish topology on 2 to the set of unordered pairs, and this is the topology that I put on graphs. And this curly sign here, G less than G prime, means that there's an injective homomorphism of graph from G to G prime. So homomorphism, so if two things are in G, or if there's an edge in G, the image is an edge. But a non-edge could be sent to an edge. Okay? Good. And now the 3 things that I would like to prove, but I'm not sure that I will have the time to prove all of this. So the 3 things is, first, if X is compact, then the quasi-order of topological embeddability is sigma 1 subset of the continuous functions from x to y times the continuous functions from x to y. This becomes false if you drop compactness of X. And second, so the point number 2 is the main part of the proof. Second, if X has infinitely many limit points, and if Y is not discrete, so at least one limit point, then the quasi-order of injective homomorphism on graphs reduces continuously to the continuous functions from x to y with topological embeddability. And third point is if x is locally compact with finitely many limit points, or if y is discrete, then topological embeddability on continuous functions from x to y is a Wellquasiorder.
X is always compact, right? X always compact?
No. So in the second point, it's true even if x is not compact. And the third point, this is why I didn't write x is compact. And in the third point, it's true if x is locally compact, so not necessarily compact. So in order to obtain the theorem from the previous slides from this one, you notice, so first thing, if x is compact, then the first point tells you that topological embeddability is sigma 1, 1. The second point, and then you have two cases. Either we are in the second point, and then because the injective homomorphisms on graph reduces continuously to embeddability, we can use the Louveau-Rosendahl result to obtain completeness. And in the third case, well, actually, point number 3 exactly tells us the other side of the dichotomy.
Do you get anything more than being WQO?
I get BQO. Yeah, I get better quasi-order.
But I mean, you don't get like some nice subclass of BQO, something that you can identify.
No.
Like you have anti-chains of any size, I assume, something like that.
Yeah. Yeah. Well, it contains. So in the cases where it's in most cases where it's WQO, it still contains, for instance, embeddability on Polish zero-dimensional spaces, and this one has a lot of large finite anti-chains. So but this is a question that we haven't looked at precisely. So.
Sorry, I still don't understand. So didn't you show on the previous slide that C of QQ with that relation has a basis of size 3?
C of QQ has a basis of size 3.
Wasn't that in the previous slide? 1Q?
Yeah.
F2,
Yeah. And
this G with that relation reduces continuously, and that means that it has many.
Q is not Polish, first of all.
Oh, but you didn't write that it's Polish in item 2.
I said explicitly in the first slide, all spaces are Polish zero-dimensional. And I
Talking about Q. But then you started talking about Q.
No. I said whenever I write a variable, it was explicitly written, and I said it. When I write a variable x, y, or z, it is always a Polish zero-dimensional space.
Q
always.
Is not X, Y, or Z.
That's an important point.
So I'm not talking about Q. This is the answer. And yeah, and I think you could maybe use the result of Lavers to prove that continuous functions from Q to Q is WQO. So okay.
I'm not sure what you would be objecting to, right? Because just having the basis result doesn't contradict anything, does it?
Oh, but if you have a huge anti-chain, you cannot have a small basis, right?
I see.
I guess, yeah.
Well, no, because he means an anti-chain under incomparability, not under incompatibility.
Oh, I see.
Oh yeah. This is a very good point. I mean, incomparability. Anti-chain is always this for me. Okay, so if there's no other questions so far, I'm going to proceed with proving point 1 and hopefully point 2. Okay.
What would be so
so terrible if you had a countable basis, not a finite basis. Somehow you feel like if you don't have a finite basis, then, I mean, I realize here you have this dichotomy, you don't even get a countable basis, but sort of abstractly.
No, abstract.
Basis would be nice.
It would be nice. It would have been nice, but this.
He just likes WQO.
Yeah.
Right?
He just likes WQO.
He likes WQOs, that's why he doesn't.
Yeah, this is the. I'm looking for a WQO on Borel function, so.
Without a finite basis, this can happen. I don't know, some context, not this context.
Naturally.
Can you show the dichotomy? You had a dichotomy.
Mm-hmm.
Of a compact space, bad or good? Yes. Okay. Yes.
That follows from what you've written here.
Yes, exactly. This is why I've written.
You already said.
Yep. And okay, so let's go with the first point. So on the continuous functions from x to y, in general, I'm looking at the compact open topology because it's the one we need to make the evaluation map Borel. And the first point concerns compact spaces. So the nice thing is that the compact open topology coincides with the uniform topology given by the metric of the uniform metric or the metric of the soup. So Ben talked about it in like 2 hours ago. So this is great because it was a great introduction. And yeah, so the distance between f and g is just the soup of the distances between the image of f, the distance of f of x and g of x for all x. And okay, so now how are we going to prove that? So we want to use, I'm going to use the remark that I gave you 15 minutes ago, that if you have sigma f and g, if you have f and g functions and sigma and embedding, then there's at most 1 tau that makes the diagram commute. So okay, so what we want to prove, okay, so now we show, yes?
It's not enough to just make sure that the diagram commutes for co-meagerly many guys in the domain?
Yes, essentially for a countable dense subset.
No, but I want to say co-meagerly because then it's just there exists f such, or there exists
Sigma.
2 guys, sigma and tau,
Yeah,
such that for co-meagerly many guys, that diagram commutes, and that
yes.
will guarantee that it's true for all of them.
But the problem is I don't want to say there exists a tau because I don't know the domain of tau. I don't want to say the domain is just the image of f. So I cannot talk about tau. This is the basic problem. So we show that the set E of sigma f g in C of xx times C of xy times C of xy, such that sigma is an embedding and so is, I'm going to write it this way, I hope it's not tau f of x maps to g sigma of x. So as I said, any sigma defines a tau that maps, any sigma defines a tau, and now we want conditions to make sure that this tau is an embedding. Okay?
F was 1 to 1. Or
No. No.
Why is tau?
well defined.
Why is there just one tau?
Why is there?
Why is there just one such tau?
Well, it's defined this way. It's defined on the image of F, right?
And if F is
But
not
if
one,
at the image of, I mean, if you give me some y in the image of F, it might have three images. So
Oh, sorry, there is at most one. Maybe it's not a function, right? But sigma has to respect. Sigma has to send points that are going to be sent to the same point to points that are going to be sent to the same point.
oh, sigma embeds F into G, or
Yes.
oh, I see. Okay. Any three images
So it's tau and yeah, I don't know, and tau F equals G sigma. I don't know. Yeah. Okay. We want to prove that this guy is Borel. Okay? And once this is done, then I'm just quantifying to say that F embeds in G. I'm quantifying existentially over sigma. So this is going to define an analytic set. Okay? Good. So
analytic would be good enough for you. Instead of delta 1, 1 sigma?
Yes, you're right. But what we're going to show is like it's going to be much less than that. So, okay. So, yes? Okay, so first thing, so we want to show that the set D, K, X, X prime, which is the set of functions f in C, X, Y that send X and X prime to close guys, such that D, the distance in Y of f of X to f of X prime is less than 1 over K. I guess, yeah. We want to show that this one is pi 0, 1 for K in N, and okay. No, I said, well, either one or the other, I think. Sorry. Sorry, what?
Maybe, I mean, Ben said less or equal, right? Instead of
yeah,
but
I wasn't thinking about it being zero dimensional.
Okay. Okay, then, so to see this, you take F. We're going to take F that's not in this set and show that a whole neighborhood of F is also not in this set. And okay, and now take F and G such that the yeah, I'm showing that the complement is open. So I'm taking something in the complement and showing that a whole ball over something in the complement is also in the complement. I'm taking F in the complement of this set.
F. This is the compact open topology.
Yes.
Okay.
Okay. And so now I'm taking some G that's close to F. And what I have is I have that the distance in Y of G of X to G of X prime, I can use the triangular inequality, and it's like the distance in Y of f of X prime minus 2 to the distance of F to G. Right? It's at least that, and this is more than epsilon. Yeah. So G is not in Okay.
Where does the epsilon come from? Is it just
No, it's not epsilon, sorry.
What is your epsilon?
My epsilon disappears because of that.
What epsilon?
Whoa, what epsilon? For some epsilon bigger than 0. Sorry.
Some epsilon.
It's just some epsilon. You take.
you want to say f is open?
Yes, I want to prove that the complement is open. So I'm taking a guy in the complements. I'm taking another guy in a small ball around it, this way, and I'm proving that this other guy is also in the complements.
But you have to distribute the epsilon appropriately.
I mean, for this
Yes, you're right. You're right. The epsilon doesn't come. You're right. Yes. Something is missing. It was written on my notes, but I just didn't follow it.
we want it less or equal 1 over 2.
No. Okay. Sorry. Then, so I forgot a line of my note. F of x prime is bigger or equal than 1 over k plus epsilon. For some epsilon.
That's false.
That is false.
Because of what I said before.
F is not in the set, so it is bigger.
The distance could be 1 over k.
It could equal 1 over k. In this
So you want this? Okay. So there's a typo in the paper. Okay. Okay, so then take G such that okay. Sorry for that.
Take G such that what the distance?
The distance of f and G.
Small, and you want to show it is contained in the complement. Yes.
Okay. Yeah, so now when I look at the distance between gx and gx prime, I can use the triangular inequality and prove that it's bigger than the distance between f of x and f of x prime minus 2 to the distance between f and g, and this is bigger than 1 over k.
Now you want straight.
Now I want straight. Right?
You should stop picking on me.
I stopped.
Okay. 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 So now we've seen point number A. Sorry for the confusion. And now B, I wanna prove that being an embedding is also simple. So as I said before, we're gonna fix a dense set, a countable dense set D that I'm gonna all the set of the dn's, and so countable bends in X. Okay, now I have that sigma is an embedding. If and only if, where am I here? So if and only if a certain horrible formula.
Wait, sorry, I lost track. B is the completeness fact? Can you go back to the
No, it's still part
No,
of the proof.
it's part of the proof now.
But this is Borel.
The completeness fact was 2.
Oh, we're not done. How embarrassing.
Okay, so for all k, there is an L such that for all m and n, I have dy of fx prime is less or equal than 1 over L, implies that dx of dm, no, sorry, sigma of dm, sigma of dm prime, dn. Okay, so what is that? This is saying that this says that sigma minus 1 is uniformly continuous. This essentially says that. Did I forget a 1 over k? Yes. Here. Sigma minus 1 on sigma of d. This says that sigma minus 1 is uniformly continuous on sigma of d. So, okay. Now, so once I give you this explanation, if sigma is an embedding, then the formula is true because of uniform continuity of sigma minus 1. So, because X is compact. Who?
Why?
Because X is compact.
Compact, so its image is also compact.
Yes. Direct images of compact set by continuous functions are compact. K is okay by compactness. And so in the other direction, it suffices to show injectivity, actually. Because an injective continuous function on a compact set is an embedding. And what we do is we suppose that it's not injective. So we take x that's different from x prime, such that sigma of x equals sigma of x prime. Then we take B, a sequence of Bm, of point Bm's in D, and C, a sequence of Cn's also in D, such that Bm converges to X and Cn converges to X prime. And we look at the sequence sigma, yeah, and we look at the sequence sigma of B0, sigma C0, sigma B1, sigma C1, etc. We take the sequence of images and we just interleave them. And the continuity of sigma and the fact that sigma of x is equal to sigma of x prime means that this sequence here converges to sigma of x, right? In particular, it's a Cauchy sequence. So now I can use this formula to obtain that actually the original sequence was also a Cauchy sequence. So it is Cauchy. Okay, and now I'm just gonna write it here. Now we use the formula the sequence B0, C0, B1, C1, etc. is also Cauchy, which is impossible because it doesn't converge. So this, okay, and this proves B. Oh, yeah, this proves B. This proves B, and it also proves that being an embedding is actually Borel. I didn't write it, but yeah. And now, okay. This is the
cool part. This is where you're going to shoot the
yeah. But actually, it's exactly the same idea as this. Yeah. So now, sigma f and g is in my set E if and only if, well, first sigma is an embedding. And we have two formulas, so, and yeah. For all k, there exists an L such that for all m and n, we have here, so dy of f of x prime, no. What did I, f of dm, f of dn, yes, is less than 1 over L, implies that dy of g sigma of dm, g sigma of dn is less or equal than 1 over k. That's the first one. And now almost the same. For all k, there exists an L. For all m and n. But now I want the other implication. So dy of g sigma of dm, g sigma of dn less or equal than 1 over L implies dy of f of dm, f of dn, there we go, is less or equal than 1 over k. Here. So this is exactly the same formula, but now instead of looking at the map sigma minus 1, I'm looking at the map that I want, which is tau. And what does tau? Tau takes an element of the image of f, and it sends it to the image of g sigma of the antecedent of, okay?
Why do you need both of these?
We need both of these because we need tau to be an embedding. One tells you that tau is continuous. The other tells you that tau minus 1 is continuous. Okay? And yeah. So okay. So now this as in the first as in the proof of B, this direction here is just compactness of the image of F and compactness of the image of G sigma. This is by compactness. Now the proof of the other direction is, suppose I have these, and you know that then you have, then one has.
Exactly the same as we just did.
Yeah. Yeah, it's just you don't have sigma now. You don't have, you have a tau. These two things here, they define a tau tilde from f of d to g sigma of d, right? One has tau tilde, and okay, that's a bijection, uniformly continuous. It's a bijection by the same thing, and it's uniformly continuous by these two things, by this formula here. And yeah, okay. And now the only thing you have to say is that on f of d, but f of d is dense in the image of f, because d is dense in X. So I have a uniformly continuous function on a dense subset of something. I can just extend it to a continuous function on the whole thing. And the same reasoning is going to tell me that the extension is continuous, injective.
So the compactness allows you to reduce arguments about continuity on the whole space
Yes.
to uniform continuity.
Exactly.
Exactly. That's what makes it Borel.
Yes.
So sigma compact would be good enough also?
Yes. Sigma compact. Wait a minute. No. Sorry. I'm sigma compact. What you have.
Because of this back and forth also too.
What you have is for sigma compact. What you have is that there is a standard Borel structure that makes the evaluation map Borel. This you have. You just use look at the space of continuous function as a subspace of the product of all the spaces from compact domain, and you prove that this is Borel. But we have an example of a locally compact space such that the embeddability is pi11 complete. It is here. Yeah, if you want, I can just write it here. Yeah. Sorry?
The relation of embeddability is actually pi11, or are you just saying it?
It was not embeddability. No, sorry, it's the set of embeddings. The set of embeddings is pi11 complete. Yeah, here. Yeah, thank you. Yeah, actually, this is a good question. I don't know in general the complexity of the embeddability relation on functions. Yeah, if X is not compact. This is what I meant when I meant what I said in general.
This is what you meant when you meant what you said?
Sorry, I had hopes to prove the whole theorem, but now I have 20 minutes left. So this is going to be the last proof. Okay, so no. Okay, so the set of sigmas in the continuous functions from n disjoint union with Cantor space into itself that are embedding. This guy is pi11 complete. And the idea, I'm just going to give you the reduction. The idea is to reduce continuously the well-founded trees on n to, let's maybe give it a name, like emb. Okay, and the map is, now you take a tree T on the naturals, and f, you map it to a function ft from finite sequences. Let me just write it maybe this way. To, this is a reduction. I'm not sure it's the optimal one. Right, I'm considering the topology and this as like another version of the Cantor space. And you map S, that's S0, Sn, you map it to itself if it's not in T, if S is not in T. And now you map it to a certain code of S, S0, 1, S0, so S0 many zeros, then a 1, then S1 many zeros, then a 1, and so on and so forth until Sn many zeros, a 1, and then omega many 2s, right? Okay? And if S is in T. Now you just notice that if B
Ft goes from finite sequences plus Cantor space.
Yes.
And the Cantor space goes where?
The Cantor space goes on itself, I guess. Yeah. And yeah, no, because it's Cantor space goes to itself. It's the identity on Cantor space. You're right. Okay. The point is, if you have a branch of T, if B is a branch of an infinite branch of T, then what you have is like the set of restriction B to the sequence of restriction of this branch is a sequence of finite sequences. It doesn't converge, but their images do. So it breaks embeddability. Doesn't converge. But how did I call it? FT. FT of Bn does. And if this never happens, obviously, if T is well-founded. So in case T is well-founded, it's very easy to check that this is an embedding. Okay.
So how do you use this in big scheme of things?
We use it here. We need to know that sigma is an embedding.
This was just a counterexample to the...
It was a counterexample to Martin's question, like, is it Borel? Is the complexity of topological embeddability between functions still Borel outside compact spaces?
And there's an understandable example where it is.
And okay, and yeah, the other thing is we also proved that the evaluation map has is Borel. So there's a standard structure, Borel structure on the space of continuous functions such that the evaluation map is Borel, if and only if the domain is sigma compact. If the domain is not sigma compact, then there is no standard Borel structure that makes the evaluation map Borel. Okay, so that was point number 1. And now for the most complex part of the proof. But okay, so yeah, I'm gonna make a drawing and explain this special case to you on an example, because otherwise I won't have time to explain the general structure. So the idea of the reduction between graphs and function that reduces the injective homomorphism to topological embeddability, the idea is very simple, but like implementing the idea is what turned out to be a bit of a nightmare.
Your hypothesis on
Yes.
part 2 did not say that in X there had to be a limit point of limit points, did it?
No, because
But your example.
my example has, but it's yeah, good question. But there's something that is a little bit frustrating for spaces of continuous functions. It's like some things go in the wrong direction intuitively. Let me just explain why. Take the restriction function that goes from continuous function from omega square plus 1 to omega plus 1, so exactly our example, to the space of continuous functions from omega squared to omega plus 1. And that just takes f, maps it to f restricted to f omega square. Well, this is a reduction. This is a reduction from topological embeddability on this one to topological embeddability on this one, even though intuitively omega square is smaller than omega square plus 1, the fact that you have a limit point there forces you to choose the image of the fact that you have a limit of limit points forces you to choose the image of the limit points according to what you did for this one.
So you just chose
So,
this because it somehow simplifies something.
yeah.
I mean, it's definitely one is compact and therefore small.
Yeah, exactly. Okay. Now, I would like just to draw what are the functions for two very simple graphs.
Can you just take the 1 point from compactification? Can you do that?
Of what?
I don't know, of your space.
Well, if you take the 1 point, yeah, but yeah, and what do you do with the point that you add? I mean, the thing is, like, it's way harder to extend a continuous function than to restrict a continuous function. And this is how you can just think of this fact here. Is that restricting is okay, extending is not. Okay, so I'm going to give you the function for the triangle, right? So just my graph. I'm taking the example of a finite graph, the triangle. What do? I'm gonna choose in my domain, I'm gonna choose 3 points, and I'm gonna look at and I'm gonna split the sequences. Right, my domain is omega squared plus 1, so I can certainly choose 3 limit points. Those 3 limit points, they have a favorite sequence that converge to them. And so I'm going to pick this sequence and I'm going to split it in as many edges as the point has. And I'm going to do the same thing here. And the same thing here. Okay? What happens on the rest of the domain is irrelevant for this example. So let's just stick with this. So this is the domain of my function. And now my function.
Limit points now, the dotted lines are something converging to it, or what?
Yeah. Yeah. The dotted lines are a sequence.
Omega plus omega and omega plus omega.
Yeah.
Plus omega, and
No, you have omega plus 1 here. You have omega plus 1 here. And you have omega plus 1 here. Every time. Okay, you have 3 copies of omega plus 1.
6. Well, no.
No, 3. Just 3.
But each of them is, the omega part is always split into 2.
It's split into 2 parts.
I was talking about the limit points. So the points are omega plus 1 and omega plus 1.
Oh, I see what you mean. Yes, exactly. Yeah, exactly. Yeah. And, okay, and F triangle just like maps this on this version of omega plus 1. And what do? I just I'm going to take these points, these 3 points are going to go on this one. And now I'm going to identify these sequences like that.
Sorry, this is omega plus 1 on the right side.
Yes. So I take omega plus 1, I split the isolated points in 3, and for each copy of omega, I'm going to identify pairwise the sequences there, the points. Okay? Okay. And the thing is, now if you look at what happens if I look at what happens if I look at the function given by the 4-element cycle? No, it's a form of coding of the graph, and there's a decoding also. In order to decode the graph, what do? You have to say, okay, the vertices or the limit points of the domain, and 2 vertices are connected by an edge. If there are 2 injective sequences that converge to these limit points, such that the images are pairwise equal. Okay? Okay.
The graph of the decoding functions, like the decoding function, the way you describe it now seems complex. I mean, it seems hard.
Yeah, but we don't care about that one, fortunately.
Oh.
What we care is that whenever you have a graph and you look at the function, that map is continuous. This is all we care. Okay? So now let me just give you the function that corresponds to the square and explain on the just waving hands to explain why these two don't compare. Okay, so this one goes to here.
Square with edges.
Yes, sorry. Okay, so what happens here? Well, you see, the thing is, first of all, that guy cannot embed in that guy. Why is that so? Because in the domain of that one, I have 4 limit points, and in here I have only 3, right? So this is, so I cannot have an embedding from there to there. Okay, now in the other direction, what happens if I try to embed that function into that one? Well, I'll have to map, I will have to map these two sequences on two sequences that are identified by the function. So I can try to do that with like these two, for instance. This corresponds to mapping the edge on the edge. And then I will say, well, okay, now that I've chosen this pair of sequence, now I'm stuck for this one. I have to map this sequence on a sequence that converges to the point of this guy, to the image of this guy, so to this sequence. And exactly for the same reason, I will have to map this sequence onto this sequence, etc., etc. And I'm going to be stuck there. So that one doesn't contain.
You can't map, it must be because you can't map the last edge, right? Because
Yeah.
there's no edge between.
Yeah, exactly. Because I'm gonna map this edge here, and so this sequence gonna map here. That one is gonna map here, and now I'm gonna say, well, I have to map this one here, and I have to map that one here. And these are not identified. Okay? Okay, so this is the rough idea of these two boxes here. The fact that there is a graph to function, homomorphism takes a graph, maps it to a function, and it's continuous. And there is a function.
We can work out an arbitrary graph given these two examples.
Yes, exactly. You can just work out an arbitrary graph. It's here.
Oh.
So.
Would you always use the same space to encode on the other
Yes.
side?
It's always from.
You only need it that you have a limit or infinite limits. Yeah.
Exactly. Okay. So this is the code of the graph to function map. And as I was explaining, there is also the decoding function that takes any function and gives you a graph. And the thing is, these two processes are inverse of one another, in the sense that if you start from a graph, you look at its function, then you decode the function, you obtain another graph. Well, these two graphs are isomorphic. Okay? So all these facts together, like, just tells you that the injective homomorphisms on graph reduces to topological embeddability on continuous functions from omega squared plus 1 to omega plus 1. Okay? Good. So, yeah, I have to skip these. Yes. Okay. Now, this was the special case. Now, in the general case, what do I have to do? Well, you see, the problem is not to manage not comparability of graphs. The problem is to manage comparability of graphs. Why is that so? Well, look at it this way. If I were to add an edge, then I would need to add sequences and etc. But I would be able to embed this function into this one. One of the reasons is that the points are just points. They're not like closed sets. So if I want now to define a function that resembles this scheme on the Cantor set, these are going to be points, but these are not going to be sequences. They're going to be sequences of closed set, and actually with a lot of points. So on the Cantor set, it's not much of a problem, because I can easily come up with a sequence of neighborhoods that are all perfect. So they're bi-embeddable. So they're all comparable. But in general, for Polish zero-dimensional spaces, if I'm not careful in doing this coding, I can just end up with choosing closed sets on which I want my function to be constant, but these closed sets are completely incomparable. So when I want to compare the graph, I will be in big trouble.
So the problem is the non-perfect
yes.
Neighborhood.
Yeah, exactly. And so the thing is, in order to do that, what we did is we came up with a notion that we called regular pseudo-embedding, and that satisfies exactly what you need. And let me maybe just draw, I'm just going to draw this because this was the last.
It's a topological notion.
It's a topological notion. I'm going to define it just now. So the thing is, so now you have your coding, and you take two functions corresponding to two graphs, right? Sorry. FH. And now you have your space X. What you can do is, well, the hypothesis exactly tells you that provided X has a limit of limit points, then it contains omega squared plus 1. In particular, you will have a retraction of X onto omega squared plus 1. So let's just call it rho, right? Rho is a retraction. The nice thing is now I have a natural map from the continuous functions from omega squared plus 1 to omega plus 1 into the continuous functions from X to omega plus 1. It's just composing by rho. And it's good because it's continuous. Now, problem. Suppose I can compare my two graphs. Can I lift sigma into sigma bar? Well, if I choose any retraction, most certainly not. Okay? So the idea is to define a very specific class of retraction such that I can do that. Right? Okay? And I can, and it's actually an equivalence. So once we're good. So let me just quickly give you an idea of what are regular pseudo-embeddings. So a pseudo-embedding, so an embedding is like when you have an injective sequence xn converging to x, then rho of xn this converges to x. So you have like if xn converges to x injectively, this happens if and only if rho of xn converges to rho of x injectively. This is for an embedding, right? Now, a pseudo-embedding is I say, well, I don't really care about injective sequence. What I care is like non-trivial sequence, non-rho trivial, right? And what is a non-rho trivial sequence? It's just defined here. It's like it's a sequence xn such that the images are eventually constant, right? So the thing is like an embedding, a pseudo-embedding is like I do not have a real objection to being an embedding, right? I don't have an injective sequence, but I'm not an embedding. Why? Because I could have a sequence that doesn't converge here, but that converges there for a silly reason. Just it's eventually constant, so it converges. I want to just like avoid this, right? So this is pseudo-embedding. So it's just an injective pseudo-embedding is just an embedding. And the very nice thing about pseudo-embeddings is that we have this proposition that comes in very handy, and like it's extremely easy to prove. So if you have a pseudo-embedding rho here, up there, sorry. Now the thing is like the only thing you have to do to find an embedding of rho into itself is you look at the image here and you find an embedding such that there is an embedding of rho minus 1 of y to tau rho rho minus 1 of tau of I. So if you have this condition, you can just naively glue all these embeddings given by the hypothesis. The naive, yeah, if it's fiber-wise embeddable, then it turns out to be embeddable, and just the naive idea works. You just take the embeddings that you have on the fibers and you glue them, and it works. And this is the key ingredient in this in this notion here. So yeah, it turned out it was not yet specific enough. So regular embedding is like condition number 3 is just this fiber embeddability, and the other conditions are to ensure that the specific format of these functions is respected. And
I mean, you could also just write down the specific retraction, right? I mean, there's no, you're axiomatizing now what the retraction has, and one would be enough. One retraction.
Yeah. One retraction that satisfies that. Yes, exactly. But then this is what we prove. So it's very easy to come up with this regular pseudo embedding when the domain is uncountable. And when the domain is countable, you have to notice that there are like up to homeomorphism only 3 Polish space with exactly 1 limit point, namely omega plus 1, the compact one, omega union omega plus 1, which is the locally compact non-compact one, and the minimal non-locally compact, which is, I just denoted omega square plus. I don't have time. And yeah, then once you notice that, you can also build regular pseudo embeddings. So yeah, and this ends up the general case. And I'm out of time, so I'm just gonna end up with 3 questions. So you've noticed that the second point of the theorem, the complexity point, is very general. X and Y are Polish 0-dimensional, and that's it. But in the third point, we know that topological embeddability is a WQO only when the domain is locally compact. What's the little problem here? It's question number 1. If you manage to prove that continuous function from the minimal non-locally compact Polish space with 1 limit point to Q is a BQO, then we could extend the whole thing. And the second question is, what becomes of the dichotomy for Baire class 1 functions? So it means if you have X and Y Polish 0-dimensional, and you look at Baire class 1 the topological embeddability on Baire class 1 functions, what happens? So obviously we already have the answer in a lot of cases, but we don't know what happens if the image. So what we know, it was recently noticed by Marx and Montalban, that if the image is omega, in the continuous case we have WQO, but in the Baire class 1 case it's sigma 1 complete. Then we also know that if the image is finite, then we have a BQO. This was done by Van Enkel and Miller and Steele 25 years ago. And so for the image, we're good. What we don't know is if you have a Baire class 1 function from a domain with finitely many limit points. If you look at the space of Baire class 1 functions with a domain finitely many limit points, do you have is this thing BQO? That we don't know. And yeah, then just a silly question. There are 2. This used to be a pi. It should be p. It's the projection. Anyway, we have 2 examples of maximal finite anti-chains, and are there more? But yeah. Okay, that was it.
Any questions that Raphaël hasn't already answered?
Or asked.
Wow. You convinced us today.
Great.
All right. Let's knock the table again.